To the afternoon session. It's a pleasure to announce the next lecture by Vybiral. Please go ahead.
So thank you everybody for coming, and also thank to the organizers for putting this meeting together and giving me the opportunity to speak here. So I changed the title slightly, but not much, and the subject is essentially the same as announced. So I will talk about approximation theory from different points of view. The work is based on joint work with some co-authors, which I will mention throughout the talk. So there will be essentially three parts of the talk. The first one is rather general, and we had already some introduction to IBC, meaning information-based complexity. So I will only go briefly through that, and afterwards I will speak about two classes of functions which we studied and tried to approximate recently. So the warning already in the beginning is that these two papers, which essentially are one for the second chapter and one for the third part, are actually pretty long and technical, so I will stay on the rather informal level and give like meta results or main ideas of all that, because sometimes the theorems involve couple of parameters and so on. So for the beginning, the story is quite old and was actually told here already. So we start with some class of objects which we would like to deal with. So typically these are vectors or functions, but might be essentially anything. And we would like to approximate them by something which we consider to be more simple or more easy to imagine or just easier to handle. So because it's only approximation, we essentially or only very rarely can really identify the objects of the interest. So we will get only quite close to them, but not to the end. So we measure the error, so the distance between what we got and what we actually wanted to get, by some distance norm matrix. We usually have only limited number of information, and there is a number of different settings which are actually covered by this pseudo theory, pseudo slide, because it's so general. It covers many settings, so I will specify that later. So I will talk about functions mostly, and they would be of D variables with an implicit stress in my talk given on D pretty large. So what is large? We heard in the talk of Henrik, it could go to hundreds. And we would like to approximate F by the knowledge, so using only the knowledge of a limited number of function values. So I will essentially talk in throughout all the slides about having some function values at your disposal and trying to say something about the original function. And there is a number of questions which were well studied in the last maybe 200 years or longer. Some of the questions are very classical, some of them like more recent, especially the dependence on D. And we go through that. So the notation was also put here. I will not use it much, so I will only go briefly through that. So the choice of the sampling points is represented by information map, which to every function in this class, which we want to approximate, gives the function values at these points. And then from these points we would like to cook up a function, say bounded, which should be very close to the function we started from. So the composition of that is we first take the function values and then we cook up something out of that. So it's the recovery operator. And the worst case error means that we want to have this approximation good for every function in the class. Of course, there is a number of different settings like average case approximation, where you don't mind that your approximation works well only for most of the functions, but there are some bad guys. The sampling numbers can be then defined as looking for the best sampling operator, so looking for the best information map and for the best recovery map. And you can put the question also in the inverse way, meaning if I want to have the error of approximation epsilon in dimension d, how many function values, how much information do I need to really be able to do that with some good algorithm, with some good choice of sampling points and a good choice of recovery algorithm. So this slide tries to summarize 150 years, which is always difficult, so I've mentioned a couple of names, but actually there should be much more here. I think one could fill a couple of slides with people who were interested in this sort of problem. And the meta result number one is that if the smoothness of the functions in the first class, in the FD, is S and the dimension is D, then at the end of the day you somehow land up with modification of the decay S over D in the polynomial. So you see that having smaller class FD of course increases the precision with which you can work, but again increasing the dimension again works against you. So increasing the dimension d to hundreds means that S has to go to hundreds in such a way that the two things somehow cancel each other. So the result which I like the most in this connection is the result of Erich and Henrik, and it's so simple that I can actually give it in nearly full detail. I mean the result, not the proof, but the proof is actually also not that difficult. So I actually recommend the paper for reading. So the question is the following. So you increase the smoothness in such a way that you cannot increase it more. In the sense you take C infinity functions. So the S essentially goes to infinity here. And all the derivatives are bounded by 1, so uniformly bounded. And the result, if you want to approximate such functions uniformly on the unit cube, is that you have no chance. What does it mean? Well, the first simple thing you can do is do nothing. So to approximate everything by 0, which is what you may call initial error. So it's like a trivial approximation, if you call it approximation at all. And the answer is the initial error is the same as the error of any approximation operator until the n goes exponentially large. So if the d goes to hundreds, you will never be able to sample that many points. So not now, not in 50 years, no matter how big computer you buy yourself. This means essentially that the problem as such can never be solved in a reasonable way. Well, there is one effect which is also quite simple and pretty obvious, but it may be good to stress it. If the dimension grows, each tiny change in the setting can result in a pretty big differences. So you know this result from like basic courses where you calculate the volume of the unit cube, which is 1, or the unit ball, which actually goes down exponentially. So in dimension 2 or 3, you would believe that the unit ball and unit cube are somehow similar of the size. But of course, if the d grows, then writing somewhere infinity or 2 can make really huge differences. And in connection with this result, the modification is if you choose the norm in a different way, then you actually get out of the trouble, and you can use some Taylor's expansion around 0 to show that in that case the number of sampling points is sub-exponential in D. So there is many other occasions where you can observe that a tiny change in the setting in big D actually makes huge differences. So now I get to, well, that is essentially the motivation for the work afterwards. So increasing the smoothness, although one could go from say infinity to analytical and to even more and so on, it seems to be a really painful way with not really potential for good and practical results. So we have seen it again already today, that instead of smoothness and tuning it up over S to infinity, it seems to be more reasonable to assume some inner structure of the function. So not to assume a brutal smoothness, but to assume that in the dimension D, which gives you a lot of space, there is some structure in the function inside, which can be, of course, exploited then. So this is based on a joint work with Heman Tyagi, and which was just, well, a couple of weeks ago accepted in constructive approximations. So what is it? So what would be additive models? So additive models means that your function f can be written or decomposed as a sum of univariate functions where each of the functions depend only on the corresponding component of the vector x. So if the sum would go from 1 to d, this would be additive models, and if we are restricted here to some small subset of all the indices, we call it sparse additive models. Sparse meaning much of the full sum is actually not there. We are left only with a tiny portion of non-zero sums here. Okay, so I will not talk about that later, but maybe it's worth mentioning that to approximate a function like that, you have easy way, which I would call, say, naive. So the functions phi's are not known, meaning they can be zero on a pretty big portion of -1, 1, and only in some small interval they can do something. So you have to sample them along some grid to be able to really be sure that they are not zero. So you can do that by starting in 0 and going along every axis, which are d of them, and some grid of -1, 1. So the number of sampling points would be the size of the grid, maybe m, times the number of the axis d. So there is an easy algorithm with md sampling points, which actually would do the job. So our aim is actually to do better later on, because this algorithm wouldn't use the sparsity here at all. So these additive models, they come with the main parameter, which I called R0 here. So this was univariate additive models, and bivariate additive models is actually a very similar construction. Namely, you have the same part as before, but you have also nonlinear functions which depend on two variables. And again, you don't know the index set as 2. And again, we assume that it's sparse in the sense you don't sum up over all d over 2 pairs. You sum up only over a small portion of them, because the others would be 0. Well, that can be easily generalized to higher R's. So you have the univariate, the bivariate component, up to the R0 variate component, meaning there is R0 variate functions which are indexed by some tuples from 1 to d and depend only on the variables which appear here. So of course the sense of the story goes lost a bit if R0 grows. So if R0 is equal to d, then of course, I mean, you didn't reduce anything. So our interest is in R0 very small, 1, 2, 3, maybe up to 5, something like that, but essentially smaller than the d. Okay, so there is two problems, and I will come to that later on even more explicitly. So With approximation theory, the question is to approximate the function, which is quite natural. That's why it's called approximation theory. But you might be very well interested, if there is a structure, in identifying the structure. And the question is, what is more important? And well, there is a close connection between these two things. If you identify the structure and you sum it up, you are very likely to land up with good approximation of your function. But it's actually not really necessary. Theoretically, one could cook up some approximation of f which wouldn't be of this form, but which in L-infinity norm would be close. So the question is, what is more important, or if you really need to identify the structure? Well, it seems that to identify the structure becomes nowadays at least that important as approximating the function itself. So that the components itself should have some meaning which we would like to really understand. So of course this is impossible if your function has more than one representation like that. So if the phi1, say, is not uniquely determined, it's difficult to approximate. So to achieve uniqueness, we need to pose some conditions. So first, it's pretty obvious that it's non-unique. So in this univariate case, it's very simple. For example, if you add up some constants to each of the phi j's, such that the constants, they sum up to 0, then you shift each phi j up and down in such a way that you don't shift the f at all. Which means, well, you have another, representation of the original function, and the phi1 up to phi something is not uniquely determined. So the easy way out is to restrict yourself to some canonical decomposition, which in this case actually has a name, and a good candidate for that is anchored ANOVA decomposition. How does it look like? So you start with some absolute term, so I didn't include it there, some plus constant here, because you could actually sample f at 0, you would know the constant, you would subtract it, and you would be fine. But in general, there could be some absolute constant as well. Then there would be the univariate components, the bivariate components, and so on, in such a way that you cannot reduce them anymore. So, for example, if I include this absolute term, I assume that every function here in 0 is just 0. If it wouldn't be, I would shift it to this constant. And that proceeds farther and farther, meaning that anytime I have a function here and one of the variables is 0, the function becomes 0. So that's briefly the anchored ANOVA setting. So for the univariate setting, so we assume, well, this absolute term, as I said, is not really important. So we assume about these functions that they are smooth, Lipschitz or Hölder-Lipschitz. And because we really want to identify the components, they cannot be too small. So if some phi would be 10 to minus something everywhere, we surely couldn't identify the index set at all. It wouldn't be a trouble for the approximation of f, because if we ignore such a small f, the error would be tiny as well. But we want to really identify all the components. So that's why we assume that at least at some point the function phi j, so every function phi j is large. And now for the scheme. So the scheme is the following. You start with points on the diagonal of the unit cube. So L goes from minus m to m, and you divide by m, so m, well, 2m plus 1 is the number of points on this grid of the diagonal. And we combine that with randomness. So we take this sort of deterministic part of the story and combine that with a random part. How does the random part look like? So we take beta to be plus minus 1 random vector in Rd, well, in 2 to the d. And naturally, by that, the beta splits 1 to d, so the index set, into two disjoint parts. The minus part, where beta was minus 1, and plus part, where beta was plus 1. And then, from every point like that, we define two other points. How does it look like? So so to every xl, we define the point x plus l with following coordinates. It's 1 if the beta was 1, it's 0 if beta was minus 1, or the minus part, it's 0 if beta was plus 1, and it's the original x if beta was minus 1. So essentially we take the xl, which is a fully occupied vector, and we erase the part which is in B minus or which is in B plus. So there is a number of ways how to write that, like multiplying with characteristic functions of these two sets. So essentially you take these points and split them into two halves. And what happens is now the following. So we don't sample the f in one of the 2 points, we sample it in both. And we subtract. What happens? So this is actually, I think, the only part of my talk where I can go to details. And it's simple and important, so that's why I do that. So what happens if you put into this SPAM, into this sparse additive model, 2 points like that? So you have, by the definition, the sum of j in this index set over x plus l and x minus l. Now you remember that phi j at 0 was 0. So anytime this guy is 0, I can leave out the term, and the same for the second sum. So anytime this thing was 0, I leave it out. It was non-zero only on the b plus set, because otherwise I just set it to 0. And this was 0 only on the b minus set, otherwise I just put it to 0. So you get a sum like that. And now you observe that the things in b plus you sum up with plus, and the things in b minus you sum up with minus 1, which is exactly the value of beta. So if I put beta j times this quantity, on this set it's this, and on this set it's this. So that's how the beta comes back into the game. So now I interpret that, so now I recall myself that I've seen formulas like that 10 years ago when compressed sensing arrived. And I interpret this as a random measurement of a sparse vector, which is what the compressed sensing situation is about. So I put these numbers into a vector z, and this would be a scalar product which is sparse because, well, this vector is sparse, so I sum up only over a few non-zero entries, and the ZL collects the values which I'm actually interested in. So these function values I need to approximate the phi j. So these I would get by sampling on axis if I would go in a very simple way, and this is how I sample them here now with compressed sensing. So it's easy to incorporate noisy sampling here because there would be noisy compressed sensing measurements, which of course is a standard part of the compressed sensing theory. One pretty big advantage of all that, so you might remember that some years ago and up to these days, I was interested in approximation of so-called rich functions, where the main idea was to differentiate at 0 and to approximate numerically the derivative by finite order differences. And of course, this is a tricky procedure when it comes to noisy measurements. So you divide by something small, the noise amplifies, and no one really knew if the things we were writing down could be really implemented in real life. So here it's much easier. So these 2 points are very far from each other. They have actually disjoint supports. So typically the distance is pretty large. And you don't divide by something else. So there is no divide by age. So actually the main disadvantage of the rich function approximation we had some time ago just doesn't appear here at all. So you have compressed sensing measurements without any amplification of divide by tiny step. So this is actually the main idea, and then you switch to the compressed sensing and you make it work. What does it mean? So we take each of the XLs, we generate for each of them the number of measurements which is necessary by the compressing theory. We repeat what I had on the last slide for each of the measurements, which means that we identify the ZL. Well, we recover by compressing approximation of that, and if some index of this vector is large, then we say, wow, this function is most likely non-zero. So we add this value into S1. So that was for us the main achievement, because once you have the support set, your problem reduced from D dimensions to S dimensions, and then you can do whatever you want. So then you can use any classical sampling scheme from approximation theory, and it's fine. So you see that the number of sampling points got down to the log D, which is the compressing result. So when it comes to bivariate setting, it gets more tricky, but it's actually doable. So if the f is of this form, so some absolute term, some univariate and bivariate term, phi's are again smooth, but actually not C infinity or something, just Lipschitz or Helder. There is some identifiability again from the very same reason, namely that we want to identify the set S2 exactly. And now, well, the thing is more tricky. I mean, what would be the simple approximation for these guys? So we would have to sample for each pair, which is now D over 2 of them, on the, well, two-dimensional grid. So the trivial algorithm, even when leaving out this part, would have D over 2 times m squared sampling points to really identify each of the functions on a regular grid. So the number of sampling points would actually grow in the dimension polynomially, which is what we would like to avoid. So we start really with such a grid. So we take L1 and L2 in minus mm, and we would be considering points like that: L1 over m, L2 over m. So these are the points from the two-dimensional grid, and we assume that we are given a decomposition of 1 to D into two disjoint subsets, and we define the points x, L1, L2 in such a way. So it's on one part of this set, it's L1 over m. On the second part, it's L2 over m. Now it becomes a bit more technical because, well, this is still the same as before. We take a random plus minus 1 vector with b minus and b plus as before, but from this one point we now cook 4 vectors. So not 1, not 2, but 4. And well, here is the definition. So depending on the relation between b plus and a1, or b minus, a1, b plus and a2, and the other option, so 4, we cook 4 points out of that. So I will not go through the proof here, but the sampling scheme is that if you sample in 4 points and you take these 2 with plus and these 2 with minus, then you are back in the compressing times. So you have the functions, well, the values which you are interested in, but with some plus minus 1 random in front of them. This seems to be good, but it's actually not that superb. Why? So we don't have independent plus minus 1 entries here, because we don't have B, J1, J2, which would be an independent matrix of plus minus 1s. We have a product of independent here and independent here, but of course they are the same on both places here. So it's essentially a random plus minus 1 rank 1 matrix here. So this makes the things a bit more technical, but there is a theory in compressing also for this, for these kinds of measurements. So we essentially reuse them with Hansen-Wright inequality. It's indeed possible to recover such a sparse vector by log D times something of measurements. So the only trick here is that we somewhere put L1 over M and somewhere L2 over M. So if I choose J1 and J2, which would be both in A1, I get only L1 over M and L1 over M on the spots. So I don't get the combination. I don't sample the phi j on the full grid, I sample it on the diagonal in R2 or unit square in R2. So for that we need a non-trivial number of these splittings, which I started here. And we need that for every index there is a splitting such that one of them lands up here and the other here. So for every J1, J2, there would be splitting such that they land up in different sets. And in this way, I will have the full information for every phi j on the full grid in R2. So for that, we need what is called hash families. By the way, the idea of using hash families comes from some paper of Devore, Dobuchi, and I forgot the other names, where it was used already some times ago and probably got a bit forgotten. So we reuse this idea and make use of them again. So essentially hash family is a family of functions from 1 to d into 1 to 2, and what gets mapped to 1 is in one set, what gets mapped to 2 is in the other set. So in that way you get bilinear measurements. Well, pretty tricky part, well, and then you combine again, you just measure for every point and so on, the number of measurements. But what is good is the number of measurements grows linearly in the size of the index set and logarithmically in D. I don't give the details on that, but it's doable to generalize to R, bigger than 2. Instead of 2, 4, you need 2 to the R0 points, which you combine with the right plus minus combinations, and you get the same sampling scheme, albeit a bit more technical, of course. So that's why I say, well, we don't want to go with R0 too far, because it's exponential in R0. So that's for the one part where I spent too much time, I guess. So the last part is only very brief. So I connected with that by saying that to identify the structure is nowadays pretty important. So you probably are aware that we all rely more and more on neural networks in essentially anything we do. And so anytime you Google something, there is surely some bunch of neural networks behind. And unfortunately, the mathematics of them is pretty tricky, and we don't, although it works, we don't really know much why. And because we would like to understand if what we are actually getting is really good, and if someone cannot fool that, it would be really great if we would identify and somehow give a meaning to the components of the neural network. So we would like to not only find a good approximation of the reality, but also understand why is a good approximation, because it can answer questions like if it's everywhere a good approximation, or if there is some fooling situations where it stops to work. So nowadays neural networks come with thousands and more parameters, and they come up by complicated algorithms without much insight about what they really mean. So in our simple model with Massimo and Ingrid, we studied very simple neural networks, so sums of rich functions, so again unknown functions and unknown directions. And the question was how to identify these components. And as I've said, it might be even more important than to identify the function itself. And you see there is this effect that we start with differentiating. This gives us something in the span of these AJs, So actually we can, after sampling the gradient a couple of times, reduce ourselves to the linear span, meaning we can reduce the dimension. So especially if the sum was sparse again, we can reduce from D to K, which might be essentially smaller. And to identify the IAs in this span, we took second order differentiation. So you see that really the numerical stability of all that becomes an issue. And then we got a span of symmetric matrices, a subspace of symmetric matrices. And the question was how to find rank 1 matrices in this subspace of symmetric matrices. And for that we proposed a non-convex algorithm which maximalizes the spectral norm among the matrices which have unit Frobenius norm. So this is non-convex, but that's actually inherited in the problem, because if you start to look for one of the A's, you have no idea which of them you find first. So actually any minimization problem here or optimization problem must have different solutions, so it must be non-convex. So nevertheless, well, there is 50 pages about that, so no details. It was possible to show that somehow you can really land in one of them after another. And with that, I thank you for your attention.
Thank you for your lecture. Are there any questions? Remarks? Comments?
For this result where you have this bilinear case with these Bernoulli vectors, so you said you apply Hansen right, and then so you first derive a concentration inequality, then you do a covering argument?
There is actually well, the result was essentially ready. So there is some paper in compressed sensing where the question was posed already, like how to recover sparse vectors like that. We had to modify, but only very slightly, the result. So we somehow repeat parts of the proof in our setting, but actually, well, I can show you the paper with all the details.
And that's the essential idea?
Yeah.
So, to your first part, if you look at those things from weighted spaces like Henrik introduced, then you basically have finite order weights with an additional sparseness condition. Is that right?
I'm not really sure about the details. So if you have finite order weights, it means you know the weights in advance, isn't it?
They are 1 or 0 somehow.
Yeah, but they are part of the problem.
They are part of the problem, yes.
So
You somehow know them in advance, that's right. But is there some connection in the results?
So we have the problem posed in a symmetric way. So we don't say in advance that the first coordinate is more likely to be important than the second or third or fourth one. So it's quite similar to the compressed sensing situation where all the things are symmetric. So I would say that somewhere down there are pretty big differences between these two things.
I guess the main difference would be that, I mean, essentially you have a nonlinear set from which you approximate, while if you start with these weights, I mean, you have a linear space.
Exactly. So it's more close to compressed sensing setting than to a linear space with finite order weights or any other weights.
I guess you could model it in that way if you take a union over spaces with, and then you have like different weights in there. So, but then it wouldn't be a single space, but like a union, and then you don't know a priori which space you're
And the union would be huge, of course. D over something components and so on.
Somehow you could combine this, right? Finite order weights, not just 1 and 0, and such unions related to
Yes,
sparseness
but I think there would be a lot of ideas necessary to push this thing through.
Okay, I guess we should stop the discussion. Let's thank the speaker again.